Thanks, Jim. All right, I'm just setting up here. Take me a couple minutes to get everything together. It's a fairly small group. I usually give these kinds of talks to smaller groups than this, so I'd like to make this one as interactive as you'd like it to be. So as I go through this, feel free to ask questions, either what's about on the slide or what's not on the slide. We could try to make this a little more dynamic than the last one. So give me a couple minutes and we'll get started. This is kind of the second non-802.11 wireless talk. Hopefully this one is going to deal with a little more practical issues. Well, I can only feed one. The last time they were tied together, apparently somebody took them off. I don't know if we have one of the support guys in the room for AB. Apparently not. Hold on. All right, should we timeshare? You get all the even numbered, you get all the odd numbered? Without an AB guy, I'm not sure what you want to do. If we could pick one, that'd be great. We're not really that crowded. Should be all right for shift the balance of the room over to this side. Sorry about that. All right, once again, if you were at the earlier talk, you understand that I was kind of asked at the last minute to talk about non-802.11 wireless. And because of the time constraint, the notes, this PowerPoint presentation did not make it into the book that you have. So the URL at the bottom of this screen has the location where you can go ahead and download that at your leisure. It'll be up, it's up right now, it'll continue to be up. All right, let's go ahead and get started. Again, I'd like to talk a little bit more practically than what I did before. The previous talk was pretty wide, covered a lot of different technologies. For this one, I'd like to focus in on a few of them and actually go into some of the details about what's going on. So we'll talk about the problems that have been encountered by some of these networks, how the industry has been responding, and hopefully some of the lessons that they've learned. If you're a wireless operator, your first and biggest concern is getting paid. You're in this to make money and as much of it as you can. So the guys who are committing fraud, what they used to call bandits, are a problem. But they're only one problem. They've also historically had a lack of trust with other operators. There's some interesting stories about how what's called clearing between operators has gotten done or not gotten done. Their second consideration is to reduce churn. Churn is an industry term that talks about people who switch providers. You'll have service for 6 months or a year. It'll be so awful that you'll switch to another one, and that provider will be just as bad as the first one. I think industry-wide right now, the churn is about 25% a year. So a quarter of all subscribers will change services within a year. Again, if you're an operator, you want to be sure that you have enough capacity. You also are now legally required to provide law enforcement with access to the traffic that's on your network. So the CALIA, the Communications Assistance to Law Enforcement Act, requires that you dedicate a certain amount of your resources to allow people like the FBI to wiretap your switch. And again, perception is everything, so you promise that people can't do bad things, and you try to keep up with all the other operators. We'll go back to our cellular model. Right now in the United States, there are basically four main types of cellular activity going on. It's got the network that we've seen in the last presentation. You have a mobile terminal that's floating around. It communicates with base stations over an air link. The base stations are all driven by some kind of control, either a switch. It goes by different names, but it performs the same function. Signaling, this will become important. When we talked about this the last session, the base station transmits continuously on a control channel. It transmits what are called overhead messages. So a mobile, when it comes up, hunts for the strongest control channel and starts decoding those overhead messages. And those messages tell it who the system is, what are the requirements to gain access, those types of things. So the mobile, when it wants access, will send in a registration message, which will contain its identity and potentially authenticating information that will hopefully convince the network to give this mobile access. The mobile then sits on a paging channel and waits for its name to be called so it can go ahead and take a call. So in analog cellular, the first generation, the authentication the information that's used to authenticate is two pieces. There's an electronic serial number that's supposed to be permanent in each phone, and that constitutes half of the identification. The other half is what's called a MIN, which is really the telephone number that's been assigned to that phone. The 10-digit phone numbers in the United States follow area code plus exchange plus the line number. Systems behave interestingly when they have MINs that don't match a legal phone number. For instance, there are area codes that you could not dial from a regular telephone, but you could program the MIN in a cellular telephone to have that odd area code. So there are some interesting things that can be done with that. In any case, that pair of authentication information is transmitted from the mobile to the base in the clear. There's no encryption on it, there's no real protection. Early on in the deployment of analog systems, there wasn't even a list of valid. All they had was a list of invalid. These were the people who didn't pay their bills. And so the quickest way is just to make a blacklist and deny them, but basically accept everybody else. Also, if you're roaming, if you were based in Chicago but you were down in Atlanta, it may have been the case early on that Atlanta couldn't talk to Chicago. So you would authenticate yourself to Atlanta, and Atlanta would let you run because it couldn't confirm with Chicago if you were legit or not. The only way that would catch up to you is weeks or months later when Atlanta sends the roaming records to Chicago and says, here's all the calls that were made that people said they were from Chicago, can you pay us for them? So Chicago can come back and say, well, that's not a valid number, we're not going to pay you for that. Historically, that was also interesting because there's no confirmation from Chicago's point of view that you really were in Atlanta. So if you were a sneaky Atlanta operator, you could populate your clearing records with some fake entries. Just saying, okay, these units from Chicago were here, pay me for them, even though the units weren't really there. All right, and as far as simple crime, because in the cellular network, it's not the person that's authenticated, it's the phone. As long as you've got the phone, you've got access. So a popular sport for a long time has been smashing car windows and grabbing the cell phone. And you'll go ahead and use it until service is canceled. Early on, that would take months and months. One of the popular ways to make money from this is if you didn't have that many people to call, you could take it to, what typically happened was it would show up in a neighborhood that had a high immigrant population, people who wanted to call overseas back home but couldn't afford to. So you'd have this guy with a stolen phone in a back room where you could go in and pay a low flat rate and you could talk to the other side of the world for quite a while. Again, somebody else is paying the bill. So those call cell operations were a big thing in the mid-90s. A little higher up the ladder in getting that authorization data and getting those ESNs and MINs, dumpster diving. You can find service activation records. They used to write them out on multi-form paper, so there'd be carbon copies. They'd keep one would go to the provider, one would go to the customer, and a lot of them would end up getting thrown out. So you could go back and find a lot of accounts that had just been activated. You could have somebody on the inside, either in a cellular sales office or in the provider's office themselves. This is kind of similar to the biker gangs that would have their girlfriends go apply to be police dispatchers so they could look up NCIC records for them. This is kind of that same idea. If you've got somebody on the inside, they can set up an account for you or a lot of accounts for you and tag them so they don't really get billed. More on the hacker side, the database itself can be hacked to insert entries, or the switch itself, that network control that drives all of the base stations. The major switch manufacturers have maintenance ports where you can go in and you can perform tests and set things up. And one of the things that you'd be able to do is establish a list of ESNs that could get basically free service. You'd tag it as a test phone and you could do anything you wanted. The next problem with the first generation and most of the second generation is that the base stations don't authenticate themselves to the mobile. The initial designs were that, well, we're the only people who can build base stations, so this is never going to be a problem. Well, what you do is you get the equipment that will transmit the identical signal to a real base station. So you provide overhead that says go ahead and register to me and authenticate yourself to me, and you simply collect the authentication information and you can then use it later. This kind of technology is used in other countries legally. Here in the United States, as we'll see, it's not legal. But if you're the owner of a theater or a church or a museum and you don't want people's cell phones going off in your facility, you get a rogue base station. You get your own cell station so that when people go into your facility, their phones will register with your base station and you just never page them. So they're camped on your signal, but they never receive a message to ring. All right, the links from the base station back to the switch are typically unprotected. A lot of places they're just microwave links that go back. So you can, if you're in line in that microwave link, you could monitor the traffic and watch the transactions as they go back and forth. Tumbling was an early system sport. It had to do with the fact, again, that Atlanta couldn't talk to Chicago. So instead of just letting everybody on as often as they want or denying everybody no matter what, they tried to pick a middle course, which was, let's let anybody make one call, but after that, we have to have authentication. So the response from the bandits was, all right, I'll program a phone that will just generate a random ESN, random MIN, so I've got random authentication, and I'll send that in, and I'll get my call, and it'll go through. But the next time I communicate, I'll give them another random one. And so you could continue to get traffic, and this tumbling is the term that the industry ended up calling it. All right, everybody's favorite is cloning. So you've been dumpster diving or you've been collecting these ESN MIN pairs. Now you've got to actually make them useful, either for yourself or selling these phones on the street. So what do you do with this? Well, you find a phone that you can get a lot of and that is easily hacked. So a lot of the phones early on had the ESN stored in what's known as double EEPROM, or electrically erasable programmable read-only memory. So when they built the phone, they inserted the ESN and then didn't expect anybody to ever change it. But of course, given the innards of the phone and the fact that the chips were standard, anybody could buy them, you could fairly easily reprogram the phone to have any ESN you wanted. Reprogramming them in is easy because every cellular service provider and every sales office has to do it anyway. Usually there's a secret code to get into the phone to do that. There was a little effort for a while to try and make this sort of legal. And the argument went that you are paying for service. It shouldn't matter how many phones you're getting service on. You know, if you've got a cell phone in the car and you've got a cell phone that you carry around in your pocket, you say to the phone company, well, I'm never going to use more than one phone at a time. Can't I just have an extension? Well, obviously the cell phone companies didn't like that, and eventually they made that illegal. But this was kind of the one segue to try and make cloning sort of legal. As they hardened the phones, the next step is instead of changing the ESN itself, you go in and you rewrite the firmware in the phone. The phone is controlled by a microprocessor. In the case of the phone that you're looking at right here, which is an Nokia 900, the firmware is stored in a PROM down at the lower left-hand side. The processor inside this phone is part of the 8051 family, which is a common microprocessor. So you can get commercial tools and simply rewrite the firmware. So the code that goes and looks up the real ESN, you replace that with code that goes and looks up your ESN. All right, the precursor to cloning is where do you get the ESNs? And this was an activity that gave scanner listeners a bad name. What you do is you have a scanner that can tune to the cellular frequencies. You tune to the frequency that mobiles would transmit on, and you camp yourself somewhere where there are a lot of cars. Good places are at the exits of tunnels, because when they come out of the tunnel, suddenly they were blocked in the tunnel. When they get out of the tunnel, now they're not blocked. They can see the base station, and they'll register themselves. So all these cars coming out of the tunnels will be transmitting their ESNs and MINs. So if you find a good place to park, you can set up your scanner. The decoder's fairly simple, and you just have software on a computer that collects the MINs and the ESNs. You just store them up and you can harvest them later. As it got tougher and tougher to do this, and you'll see why it got tougher, the next sport was just, okay, I'm going to be a legit person, but I'm going to sign up under a false identity. I'm going to have a fake ID, or I'm going to try to use some way of getting service and just not pay the bill. Session hijacking is a weakness that still exists, but it takes a little bit of work to get done. You've got to understand a little bit about how phone calls go on. When a phone call is established, the cell phone and the base station have agreed on something called a supervisory audio tone. There's only 3 of them. The original idea was to try to separate legitimate calls from each other. So what the hijacker does is listens to a conversation that's going on and decodes the supervisory audio tone that's associated with this call. Many phones have this feature in firmware. So you determine the supervisory audio tone, then you program your own phone to generate that same tone, and you get yourself physically closer to the base station, or you use a higher powered transmitter, and you can take over the call. So the hijacker will, by turning on his transmitter with the matching tone, the base station will ignore the legitimate phone, which has a weaker signal, and use your phone, which has a stronger signal. At that point, you can flash hook, you get your own dial tone, you can go ahead and make your own calls based on the authorization that's already been done by the legitimate phone. Are there any questions on any of this? It's a pretty quiet audience. Either one. All right, so the industry responded with attacks in a couple different ways to try and cut this down. The first was the legal approach. So they went to Congress and demanded that Congress pass these laws that force the FCC to make certain things illegal. So now it's not legal to tune to cellular frequencies. It's not legal to listen to it. You're not allowed to clone things, and they've even gone so far as to say you're not allowed to own the equipment that you might be able to use to clone a phone. On the technical side, they ran through a whole bunch of things that didn't really work very well. The first was asking for pins. So when you made a call, it wouldn't connect you right away. You get this automated voice that says, please enter your PIN. And so you type in this 4-digit number on your keypad, and then you get connected. Well, customers hated it, and it wasn't very secure, because if you've already got a scanner to grab the pairs, you can listen to the tones as well and decode those, and now you've got the PIN. The second was something that the industry calls velocity checks, which is if you showed up on the south side of town 5 minutes ago and now you're on the north side of town, something's not right here. Again, as it says here, that works for roaming if you show up in Atlanta and then you show up in Chicago. But it took some time to tweak how fast is too fast. The follow-on to that is, okay, you can't have the same ESN and MIN active in the system at the same time. That's good for stopping it, except the legit customer also gets cut off, and he's not very happy about it. One of the more interesting technologies was RF fingerprinting. Each phone is, even though they're coming off the same production line, there are minor differences. The parts that get put into each phone are slightly different. So the characteristic of the transmitter inside the phone is slightly different from phone to phone. The idea of RF fingerprinting is to capture that when the phone first comes on with a legitimate customer, you capture that fingerprint. And so then subsequently, every time that phone turns on, you compare the fingerprint you just got with the one that's on record. If they don't match, you deny the call. All right, all those were kind of stopgap measured until the authentication, what the industry called authentication, comes along. And the idea in both the US systems and the GSM system is what's called a challenge and response. The network sends a challenge to the phone's got to do a bunch of work with some secret things and send back an answer. So on the US side, there's 3 sets of algorithms. As you can see here, one provides numbers for everything else. Control message encryption algorithm protects basically the things you type on the keypad, and the voice privacy mask is supposed to give your voice calls a level of protection. On the GSM side, those roughly correspond to what are called A3, A8, and A5, and those are 3 different algorithms that GSM uses to basically accomplish the same thing. All right, in the US, the phone itself and the network share a secret, and that secret is called an A key, or the authentication key. That is supposed to never be revealed. It never goes over the air. It's the big secret to keep. What they use instead, what actually goes over the air, is something called shared secret data. So from the A key, you derive shared secret data, and then you can trade the shared secret data over the air, and you're not as worried about that because that changes. The A key never changes, the shared key data will change. What you do is you take this data, and you'll see how in some of the next slides, and you generate an authentication message, which is 18 bits long. It's big enough that it prevents the problems that they were trying to address. So if you're running this in your system, there's 2 different kinds of challenges you can have. You can uniquely challenge an individual phone. They say you can challenge a phone at any time, but typically it only happens when the phone attempts to make a call. And we'll see how that works. The other is a global challenge, which goes out on the control channel and tells the phone that basically whatever you try to do, I'm going to authenticate you first. So you're going to have to do all this work before you can register with me or make a call or get a call. Okay, so in the process of authentication, the phone signals the network and says, okay, I want to make a call, and I am capable of doing authentication. There are still old phones in service that can't do authentication, and the cellular service provider has to figure out what to do with them. Typically what they do is intercept it, and you get a nice lady on the phone who asks for your credit card. So if you can do authentication, the switch goes back to what's known as the home location register, which is wherever you're based out of. So again, if you're in Atlanta, the home location register will be in Chicago, where you originally got your phone. The mobile switching center has different capabilities. Some can actually do the authentication work themselves, others of them can't. So you indicate, so the MSC here will either do the work itself, or it will tell the authentication center, hey, you've got to do all this, I can't do it for you. So what happens is the authentication center or the MSC generates a random number, and they send it to the phone. The phone then runs that cave algorithm that we saw with the random number, with the shared secret data, with its own MIN and its own electronic serial number, and it produces its version of the authentication number, sends that back to the network. Meanwhile, the network has also run the same algorithm on what should be the same data. So it generates a local version of this same authentication number. So if the two numbers are correct, the assumption is that all the underlying data is the same. They have the same random number. Most importantly, they've got the same shared secret data. All right, the shared secret data is not supposed to stay static for the lifetime of the phone. There's supposed to be updates. So this procedure doesn't authenticate the phone, it just updates the shared secret data that will be used in the authentication procedure. Again, rather than just go through step by step, I'm sure you can read it just fine too. There's another variable that appears to be used by some systems and not others, and this is a kind of a double check on whether this unit is a clone or not. There's this count variable that the authentication center can tell the phone, okay, bump up your count. Originally, it was supposed to be done on every call attempt, but it doesn't have to be. And the idea is that those counts need to match each other. If they don't match, the assumption is you're a clone because you don't know what the right count number is, and your service is going to be denied. All right, the weaknesses in this. On the back side, as in most networks, the links between, say, the base station and the switch and the authentication center are typically not protected. Those are open networks where you could sniff to get the data out. You could also, again, use those database attacks to pull information out of the home location register, the visitor location register, other places in the network where this secret information is passed through. A few years ago, Bruce Schneier and a group of other people published an attack on CMEA, which protects the key side. So there's the feeling in the air that maybe these algorithms aren't as secure as they hoped they would be. The keys are small. When the authentication keys first came out, some of the phones had bugs in them, so they wouldn't accept what should have been the proper A key. So they had to take a certain kind of A key. So that would cut down on anybody's search time to try and brute force it. Other operators used A keys of the equivalent of all zero. Every phone in their network has the same A key. Another problem on the voice side is that when the algorithm is run to generate the voice privacy mask, the mask that it comes up with is the same for the life of the call. So from beginning to end, you're just exclusive ORing the voice data with the same mask over and over. And so if you've got known plain text, you can find out what the mask is and you can pull out the voice data. And again, the cartoon is there to indicate that the random numbers that go out there have been suggestions that they may not be so random, that you may be able to actually predict the numbers that are going to come out for these challenges. All right, on GSM, GSM tried to do things right. They separated the user from the equipment, and there's two different identification numbers, one for the hardware side and one for the subscriber side. The hardware number is supposed to be burned into the phone itself. The subscriber information sits on a little smart card that they call a SIM. The GSM, again, they've got, just like in French, they've got different names for everything. So here's their version of what all these things do. Their version of the mobile is both the hardware and the SIM. Base stations are BTSs, and BTSs have controllers and they talk to switches. But it's, in essence, it's similar to what we've already seen. This comes from the head of the MOU security group, where he spells out what the security goals. He wasn't going to make it perfect. He was going to make it the equivalent of the wired network. So he wasn't trying to make this completely secure. He just said, we're going to be as good as the PSTN. He also notes that as he says here, the technical features for security are only a small part of the security requirements. Basically, there's other problems. Whenever you've got people in the loop, there's going to be a problem there. One of the things that GSM does is provide anonymity, or supposed anonymity. The idea there is that instead of broadcasting your ESN and the equivalent of your MIN all the time, when you first connect to the network, it will give you back a temporary identifier that eventually will change, so that as you're hopping around the network, you're communicating with a temporary identifier. So anyone who is trying to correlate your activities over a long period of time wouldn't be able to. So GSM's authentication. Again, they generate a random number, and that random number goes both on the network side and on the mobile side. On the mobile side, it runs A3 and A8. In most systems, that's one algorithm, even though in the documentation they show it as two. You feed something called KI, which is a secret piece of information that's held in the SIM and held at the authentication center. That's the shared secret between the two. A3 is the authentication side of that algorithm. It produces something called an SRES, or a signed response. And that, this is going to look like the other one, but basically you generate a signed response, you send it back to the network, and the network checks that your answer is the same as its answer. If they're okay, you're authenticating, you go ahead. The other side of that is A8, which takes the same data but produces something called KC, which is a cipher key. And that cipher key is fed to another algorithm that's called A5. There are different versions of A5, but A5 will protect the actual voice traffic that's occurring over the air. Are there any questions on this? Is everybody just waiting for the gala? Nothing? Okay. All right. That A5, we kind of talked about some of this. That A5 again is supposed to be the privacy side, and there are multiple flavors of A5. The first one that came out, well, let me step back. GSM was developed in Europe during the 1980s. The biggest threat then was the Soviet Union, which was right next door. So as they were designing this, they said, look, we need a privacy algorithm that's going to be good for us, but as we export GSM to these maybe not so friendly countries, we want an A5 that's not so hard for certain people to break. So they came up with a family of them. Let's see if this is the next one. Okay, there's A5-1, which is the first one that came out, and that was originally spec'd only for Western European countries, and that was supposed to be the strongest of the two. There was A5-2 then that was deliberately weakened, so you could field phone systems to places like Syria and Iraq. And you wouldn't necessarily have to have access to the network in order to eavesdrop on the traffic. There's also an A50, which is basically no encryption. All right, well, all the algorithms that we've talked about, basically all of them have problems. It turns out that the A3-A8 combination is called Comp128. And what happened was the GSM MOU group, when they put out the specifications, said, okay, all you operators, here's an example of what you can use for A3-A8. You don't have to use this, but this is what it should look like. So what did the operators do? But they used the example. They said, okay, we're going to use Comp128, and we're done. Well, it turns out that if you feed Comp128 the right kinds of questions, it'll begin leaking bits of this KI, this secret number that you're not supposed to let anybody know. So if you run Comp128 enough times with enough information, you can recover all of KI, and you've lost your security. It also turns out that A8, the part that feeds the cipher key to A5, it doesn't really, even though it generates 64 bits, 10 of those bits are always 0. So its effective length is much smaller, which there's suspicion that that was done in order to make the cracking easier. A5 itself, we've already talked about. It's basically 3 shift registers where one of the shift registers controls the clocking of the other 2. So that the key that comes out of A8 plus the frame number of the TDMA frame that you're on generates the protection. Again, the same rogue base station that we saw in the early US cellular systems, same things in GSM. You could create a rogue base station, and in fact there are things called MC catchers that are basically rogue base stations that will follow the GSM protocol and exercise a phone. As it turns out, you can use an MC catcher to exercise the Comp128 leak, and so potentially you could get KI over the air without even touching the SIM. As we've discussed, the network links on GSM are also unprotected. You could join that network and ask the authentication center for more of these triples and use them for your own purposes. As it also turns out, the implementation of some of these, KC doesn't necessarily get changed after each call. The KC may be used for a while. So again, if you're able to capture that, KC may be good for a period of time. Yes, go ahead. I'm sorry? A52 was the lower level. A52 was designed for export to potentially unfriendly countries. North America, I am told, uses one of 2 things. It either uses A52 or it uses nothing. All right, all this talk about where does this information sit. The phone itself does A5, that's in hardware. But the authentication and the code that generates the cipher key is done in a SIM card. And this is basically a little computer on a wafer. The interface pins are well documented. There's a standard that is used to talk to smart cards. A SIM is just one kind of smart card. There's smart cards that do a lot of other things. So this is actually physically how to talk to it. For a GSM SIM, there's a specification that fully spells out all the things the SIM is supposed to do. It lists the instructions that the SIM is supposed to follow. When you talk to the SIM, there's a class that you have to provide, and for GSM it's always A0. The actual instruction that you want the SIM to execute, and then the parameters for it. It's interesting to probe SIMs for undocumented instruction codes. There are almost always codes that the manufacturer uses to test them, either in design or in production. So there are codes that are not documented but sometimes do interesting things. Depending on the SIM card reader you're using, there may be additional overhead that you have to wrap around it, a command to get the reader to tell the SIM card to do something. So you send this command to the SIM, and then the SIM is supposed to answer you. And the SIM will come back with information, if there is any that you asked for, and then 2 status bytes. So it's a fairly simple protocol. So for a GSM, this is a set of commands that it will understand and know how to operate. The SIM itself maintains little bits of information in a hierarchical file structure. So you see the read records and update records. Those are ways of accessing information in each of those files. The CHV is the verification code, which is another name for the PIN. In SIMs, there's the PIN that you get, and then there's a PIN that the system operator gets. So if you try your PIN 3 times and then you get locked out, the service provider can put in their PIN to unlock your PIN. So there's actually 2 of those. The function that we're focused on here is down near the bottom, which is the run GSM algorithm, that 88 command. That executes A3, A8. In most cases, that's Comp 128. So let's take a look at how we talk to a card. The first thing you do is you power up the card and you send it a reset. And what you get back is an ATR, or an answer to reset. And that data tells you about the card, tells you what it is, tells you how to talk to it and what to expect. So then you say, okay, I want to look at the directory structure of the SIM. So you request to the SIM, I want to look at what's known as the master file, which is kind of like the root directory. And that will tell you what's in there and everything else that's going on. So the underlying data in blue is decoded for you underneath there. So when you read that file, you get a file header and it tells you what's going on with that master file. Here I want to read a dedicated file. There is a dedicated file, which is like a subdirectory just for GSM. So again, we can decode the answer that comes back and it tells us about that file. Here's an example of how to read the subscriber identity out of it. You ask for what's called an elementary file, which is kind of the lower level leaf file. And it's got the same kind of header, tells you the information that's going on. And down at the bottom, we actually read it. We issue the read command and we get the MC back out. So now we want to actually run Comp 128 on the SIM. So we open up the GSM file, and then we do the computation. We give it the input data, and then we tell the unit to actually run it. It comes back with those 2 pieces of information, the cipher key and the signed response, that come back in that package, and those are what actually gets used. So if you want to take advantage of the leak in Comp 128, you'd perform the computation and you'd capture the data time after time after time, feeding it the correct data and getting back out the response and computing the value of KI very slowly over time. Okay, so the repeated attack was public several years ago. One of the changes that SIM manufacturers have started to do is put a limit on the number of times you can actually run the authentication algorithm, which kind of puts a damper on the first method of pulling the SIM out, or pulling the KI out. That's not the only attack that SIMs are vulnerable to. There are side channel attacks that actually work for a variety of smart cards. Side channel attacks are defined as an attack that's not on the interface itself, but it's another characteristic of the card. One of the first analysis was done on power consumption, that if you look at the changes in the power that the card is consuming, you can tell how many gates are active, which tells you which part of an algorithm it's running. And by being sophisticated about what you're looking at, you can determine what's going on. Timing was a similar thing. The latest thing was a paper from IBM who's basically watching, who they essentially they laid an antenna across a SIM and monitored the electrical fields that were coming out of this. And they were able to read out KI in, I think, eight actual executions of Comp 128. So there are different ways to get at it. In response to these problems with Comp 128, the industry has come up with 3 different things now. They came up with a 128-2, which was supposed to fix that bit leaking. They came up with the -3, which doesn't always return those 10 bits of 0 at the end of the cipher key. And then they decided, okay, this really isn't getting us where we want to be. Let's replace A3 and A8 with a public, a derivative of a public algorithm, and we're going to tell people about it, which is a big change for them. None of this is going to be cheap because the A3, A8, as we saw, sits on the SIM. So every subscriber, if the operator is going to use these new methods, they have to replace all the SIMs. They also have to update their software, which isn't such a big deal, but finding all the customers, getting a new SIM, getting the customer to put it into the phone is a big challenge. All right, A53. The MOU also figured out that since the A5 algorithms are now public and the weaknesses are disclosed, they decided we're going to come up with a new one that's going to be better. They're going to base it on a public algorithm, and they're making the specifications available. You can go there and download the specs yourself and see what they're going to do with it. So they're moving in the right direction. Okay, I talked a little bit about this. If you're a restaurant owner or a theater owner and you don't want people's phones going off in your place, you can, not in the United States, but in other countries, you can buy a cellular, what they call a cellular jammer. It's a base station that will capture the phones. The FCC basically said, we don't allow this. We've licensed the cellular providers to provide their service to a geographic area. We're not going to allow you to do this kind of thing. So in the U.S., they're illegal. In other places, they're used. All right. So before we get into satellites, are there any questions on the terrestrial stuff? Is there anything that you'd like to ask about before we switch to satellite? Okay, if you program a phone, this is going to depend on the system, but if you program a phone with a MIN that has, let's say, an invalid area code, typically those phones would be issued to employees of the phone company. So they would, when the switch sees a call, it can do a number of things with it. So that the switch will see this MIN come in. It can either treat it like a regular phone, it can deny it, as you suggest, or it can give you access to other features. One of those is the ability to exercise the switch. So you can run through a series of tests on the switch. You can essentially take the channel that you're on out of service. You can say, it's basically telling the system, I'm a technician, I'm going to test this link, and so you can take it out of the system. Other phones have been set up for corporate executives of the phone company where it's just not billed. You could talk all day and all night and no billing record would ever be generated. Those are the kinds of things that they would do with what are known as illegal MINs. Yes, go ahead. Okay, if I understand this right, you had a phone, a GSM phone in Norway with no SIM in it that was making phone calls on its own. that correct? Apparently. I'm sorry, didn't have a what? So the phone had no battery either? Okay, the phone was not making calls then, and that's pretty simple. Well, it's interesting to try and deal with phone companies on that, because their position for a long time has been that GSM phones cannot be cloned. Therefore, if there's any activity with your number on it, it's got to be you. There's no other possibility. And so obviously that's not the case in fact, but that's how phone companies treat it. But yeah, if it's got no battery in it, that's pretty straightforward. Okay, on to satellites. Not sure how much time I have left, but I'll try to get through what I can. Satellites, there's a bunch of different kinds. The newest things are LEOs, the low Earth orbiters, and I'll try to spin these through as quickly as I can. The LEOs, as defined by the FCC, are satellite constellations that provide voice service that operate above 1 gigahertz. Most of the satellites up until the LEOs were put into orbit would be much higher. They'd be 22,000 miles up, which is high enough so that as they're orbiting the Earth, they're orbiting at the same speed the Earth is rotating, so they appear over the same spot. The idea with LEOs is if we've got the satellites a lot lower, a lot closer to the Earth, we'll be able to get signals to them much more quickly, and we'll be able to have more capacity. So essentially these LEOs are the cellular base stations in orbit. There's a network of ground stations around the world that talk to these satellites as they go by. These are typically linked back to a network control center where they provide service. The LEOs have their own frequency allocations from the FCC, and these are what they are. Iridium probably got the most press, $5 billion, and 15 years later they went bankrupt. 66 satellites in orbit. They do go pole to pole. The annoying thing for people in the satellite business is that all those satellites do processing on board, which means when your phone powers up and you talk to an Iridium satellite, the satellite is answering back to you. What happens in most cases with most satellites is that there's something called bent pipes, which is they simply repeat whatever they hear from the ground. In the case of Iridium, they decided not to do that. So on board each satellite is the ability to process calls, and that'll turn out to be important for one of their customers, which we'll see in a minute. Iridium also managed to bully the FCC into giving them their own slice of the allocation all to themselves. So it's basically they had a certain amount of space. Motorola came in and said, we've got a lot of money, we're big, we're going to take half of it, and you'll leave the other half for the other 4 applicants that were applying at the same time. Iridium promises that they can provide 2.4 kilobit data service. Yeah, maybe. They ran for less than a year before they ran out of money. They didn't have nearly as many customers. They had less than 10% of what they projected, so they went bankrupt. What happened was another group of investors came along and for $25 million bought everything from the bankruptcy court. They reestablished service basically on the strength of a 2-year contract that they got with the government. So out of this dedicated Earth station in Hawaii, the government is getting service off the Iridium satellite. The big reason that the government likes Iridium is that the satellites themselves can communicate one to another, which is unusual. Most satellites only communicate with the ground. In the case of Iridium, they communicate with each other. So if you're in Abu Dhabi, you can make a call up to an Iridium satellite. It bounces from satellite to satellite until it lands in Hawaii. And for the government, this is a very good thing because they don't trust anybody else's gateway. So the only thing so they want to protect the call. They believe that this is the best way to do it. Otherwise, they would have to go up in Abu Dhabi and come down somewhere in the Middle East and then go by landline back to the States. and the government does not want to do that. So because of this capability, they're willing to pay this new group running Iridium a big pile of money, and they seem to be fairly happy with it. There's a long-term issue with Iridium, which is, are they going to be able to make enough money to replace the satellites as the satellites begin to wear out? And so that's still not clear. Iridium claims that their satellites will last, that the ones that are in orbit right now will last another 8 years. By then they'll have enough money to replenish it, and it's not a problem. Not everybody agrees with that. Globalstar is another big LEO. This one got a later start than Iridium. Other satellite folks are a little happier with this because these are bent pipe satellites. So not only are you able to run the CDMA service that Globalstar itself is providing, but potentially you could buy capacity on the satellite. You could run your own signals over it. There was some complaints early on that the satellite design did not provide sufficient power. That's one of the main things that counts when you build satellites, is the amount of electrical power that's available, so you can run all of your amplifiers and you can move all the signals that you want to. There was an argument that the Globalstar satellites were not powerful enough to serve the kinds of purposes that they wanted to. Globalstar is promising 9.6 kilobit. They don't really have all that many customers, so that the power issue and the capacity issue so far hasn't been a big deal. ICO is a London-based setup that their difference is they wanted to put fewer satellites and they wanted to put it into what's called a medium Earth orbit, which is kind of halfway between the low Earth orbit and the geosynchronous. Still gives you the benefits of a much shorter path, still works with lower powered units on the Earth, and you can get away with having much fewer satellites. ICO was talking about a 10 satellite constellation. They are going to be GSM based, their protocol. ICO also went bankrupt, and they were then invested in by Craig McCaw, and the idea now is to merge it with the teledesic plan, with the Bill Gates Internet in the Sky plan. All of this is kind of both in flux and in hold because of the failures of Iridium and Globalstar. So there's not really right now a lot of excitement about these kinds of wide bandwidth satellite. All right, after the big LEOs, there is something called little LEOs, and the FCC defines those as data-only services that operate below 1 gigahertz. The one there's only one that's really in real operation. That's called Orbcomm. They also went bankrupt, and they were also bought by investors, and they are continuing in operation. 28 satellites in low Earth orbit. They operate in the 130 to 150 megahertz band, which is also a paging band, which can create interference problems. The Orbcomm model of moving data is basically by email. Yeah, go ahead. Yeah, the satellite that went out, it was not related to little LEO, but I'll get to that. That's on a slide later on. Orbcomm's idea of moving data is based on email, and the satellite itself can store these email messages. It can get it from a subscriber that can be anywhere. The satellite will hold it until it gets over a ground station and then download it. What that incurs is a certain latency. It can be many minutes before a message, before the total time from if you're a subscriber and you push send to the point where your recipient gets it, that can be many minutes. Mobile Satellite Ventures is a voice and data supplier in North America. They've got 2 satellites. One's basically a Canadian satellite, and the other's a U.S. satellite. What you're seeing there is what's called the footprint. There are 6 beams off this satellite. Alaska and Hawaii count as 1 beam, and they cover the United States. Okay, on these satellite links, satellite providers are not immune from CALIA. So the same not quite the same intensity, but the FBI has demanded that all these service providers give them the same kind of access that they would get from the telephone providers. So there's been an agreement with each of the providers. TMI is the Canadian side of mobile satellite ventures, which created an interesting issue. The FBI was going to prevent TMI from selling service in the United States because they were afraid that a U.S. person could go to Canada, buy a TMI phone, use it in the United States, and it would not be tapped because FBI wouldn't be able to go to Canada and get it. Well, TMI finally agreed that, you know, okay, we'd let you in if it was a really good reason, and the FBI relented. For most of these systems, there's test equipment that will use it because it's not the kind of popular thing the regular cell phone is. There isn't a lot of encryption on these systems, and the phone equipment that you can get tends to be modifiable. Intelsat actually got some interesting press recently. It started out as a group of countries that got together and decided to build really big dishes so they could move telephone traffic back and forth. Then they got into television. What you may have seen on CNN a couple months ago was live video from the unmanned aerial vehicles in Afghanistan. The data was being brought back to the United States on an Intelsat satellite that anybody with the right equipment, and it's not much equipment, was able to watch. So it made for interesting TV. Inmarsat is another international organization, but their focus is on the marine side. They started out serving shipboard people, but now provide L-band mobile coverage. The AOR is the Atlantic Ocean region and Pacific Ocean region, Indian Ocean region. They started out covering the oceans, but now basically cover the whole world. Inmarsat is struggling with some of the same things that the cellular industry early on struggled with, that the Inmarsat phones, they have a significant number of cloned units, and they're having a hard time tracking them down. GPS, I'll just go through this briefly. This, again, is a satellite system that most people can't talk to, but will listen to. The biggest thing about GPS in the last 2 years was that something called selective availability was turned off. It used to be that the government deliberately degraded the signal quality of GPS so that you couldn't get as accurate a position as you can now. GPS can be jammed and it can be spoofed, and those are things that are worrying the FAA because the FAA wants to begin using GPS for precision approaches. The military has reserved the right to jam or spoof GPS in areas of conflict. They haven't particularly described where those areas of conflicts may be, but right now you can probably make some pretty good guesses. Here's a list of GPS frequencies. The main one that all of the commercial units use is the first one, which is called L1. It's in the L band. It provides what's called course acquisition, and it gives you the commercial level accuracy, the 30-meter accuracy. If you are an approved user, it doesn't necessarily have to be military, you could be a Department of the Interior, and you could get the equivalent of a GPS, but a military version. On that second frequency is a code that's correlated to the course acquisition, but it's called precise, and it will give you much better accuracy, 10 meters or better. In times of when the Pentagon's excited, they'll encrypt that, and then they call it Y code. But the military receivers are able to decode that and still get the information. Since they were going to the trouble of launching all these GPS satellites are in low Earth orbit and they're watching the Earth, they decided to put on board another sensor that would allow them to detect nuclear detonations. So there's another signal that comes down from these guys that provides that information. L4 is a correction signal. One of the biggest inaccuracies of GPS comes because the ionosphere changes from hour to hour and day to day. but it changes differently depending on the frequency. So what they suggested was, let's send another signal at a higher frequency and we'll be able to even out the issues with the ionosphere. And they're also talking about L5 as a way of getting even more GPS accuracy. As the military is looking at what they're going to need to do in the next few years, the next follow-on program is something called M-code. M-code will be an encrypted signal that will address some of the shortcomings that they found so far related to jamming and spoofing. Now, GLONASS is the Russian equivalent of GPS. It probably works as well as Russian automobiles do. The actual system, I'm told, was only fully operational once, and that's because Yeltsin told them, let's make it work. Let's make all the satellites work at the same time, at least one time. Most of the time, several satellites are out of service or providing bad data. But when you read the press, everybody talks about building GPS receivers that use both GPS and GLONASS. I'm not sure why they do that, because GLONASS isn't providing what you would hope it would provide. All right, here's where we get back to your question, and this goes back to risk, because satellites do fail. The Galaxy 4 that's listed at the top was probably supplying close to 80% of the paging towers across the country. So when that went belly up, all of those paging towers subsequently did not have any paging data. So all the pagers weren't able to receive the data. As you can see on the list, other satellites have failed in some spectacular and some not so spectacular ways. But there are definitely risks in counting on satellites to be there, as you can see here. Okay, that's it for what I've got here. Looks like we got a couple minutes. If there are any questions. Good point. As usual, I'll be happy to talk to you after. Otherwise, have fun at the gala. Thanks.